Alright, so today we'll talk about isomerism, and we'll do a little lab and look at different molecules and see if we can understand isomerism in much better way. Okay, so the first isomerism that we talked about in the class was configurational isomer, okay, or structural isomer basically. Yeah, and so as an example, I have taken one butanol and two butanol as an example, and so this is the molecule of one butanol. Now remember that structural isomers have same number of carbon atom, and the number of atoms and the atoms are same in the molecule, so that means the molecular formula is same for the molecule, but they differ in how the atoms are arranged. Okay, and that give rise to structural isomerism. So here we have one butanol, and you can see how it looks. Okay, do you guys see it? So CH3, CH2, 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 OH. Okay, the red one is oxygen, and these ones, the gray ones, are carbon, and the white ones are hydrogen. Okay, obviously they are not according to proportion of their sizes, but you get the idea, because you see that this hydrogen is much smaller than this hydrogen. That is usually not the case, but you get the idea that atoms are slightly smaller or larger. Yeah, now you see that this molecule is not straight in the way it is usually shown in your books. Yeah, it is zigzag. Yeah, it goes up and down, up and down, and you see that it goes up and down. It's not straight the way it is usually shown in your books. And the reason for it, as we'll study in the next year, basically why this is the case, the reason is because carbon has a specific requirement. Yeah, let's put it like this: carbon has a specific requirement. It can make 4 bonds. Okay, and these 4 bonds, there is a theory called valence bond repulsion theory. Yeah, according to this theory, these 4 bonds needs to be equally spaced from each other. Yeah, and the only position, or the only way these bonds can be equally spaced from each other, if they have this type of structure. Okay, so one bond is here. So 3 bonds will make like or 3 atoms will make a base of the pyramid, and one atom will make the top of the pyramid. Okay, and what that does is basically, now the bond angle, between this hydrogen and this hydrogen. So if you count hydrogen, carbon, hydrogen, if you count this bond angle, that is going to be about 109 degrees. Okay, if you count this hydrogen, carbon, and hydrogen bond, it is going to be the same. Yeah, it's 109 degrees. If you take this carbon, this hydrogen, carbon, and this carbon, and if you count the bond angle, it's again going to be around 109 degrees. So there is going to be a slight difference in the bond angle depending upon which atom is connected to. There is going to be a pull and push effect, and so but it is going to be about that much. Okay, so on an average the bond angle is going to be 109 degrees. Is that clear? Okay, that's 109 is the natural bond angle for carbon when it is singly bonded. Okay, if it is a doubly bonded, then, and we'll show when I'll show you the alkene structure, then the bond angle, or the natural bond angle for carbon, would be 120 degrees. Okay, if it is triply bonded, then the natural bond angle for carbon is 180 degrees. Okay, 180 degrees. So the molecule is linear. If you have a triple bond, and you see that we saw the alkyne molecules, correct? If you remember, alkyne molecules are linear. Yeah, all the atoms are around that triple bond are arranged in a single line. Yeah, you don't see that in here. This is called as tetrahedral arrangement. It is because if you look at one, if you let's say if you take just one, and let's call methane. Okay, because that is the simplest and you see that this is a methane, yeah, and you see that this is a carbon. Now here again all the carbon, hydrogen, or sorry, hydrogen, carbon and hydrogen bonds are identical. It is 109.5 degrees. Okay, and this is called as tetrahedral arrangement because this is a tetrahedral. If you draw the lines, if you connect all the hydrogens, you get a tetrahedron. Yeah, you guys probably have seen or heard tetrahedron in geometry, I guess. I don't know what they teach in ninth grade anymore, but it's probably, you know, that the tetrahedron is has a pyramidal base, yeah, and has a pyramidal top. It's a pyramid basically, yeah, and so the base is called a pyramidal base and have a top, and if you connect that if you connect all the atoms, then you get a tetrahedron. Okay, so this is your methane. Yeah, and so this is the bond angle, natural bond angle for carbon in the state when it is singly bonded. As I said, 109.5 degrees. And if you see all the molecules that has carbon and it is singly bonded to any other atom, the carbon will always have a bond angle that is close to 109 degrees. Okay, there are variations. It could vary from 4 or 5 degrees up to 4 or 5 degrees depending upon the nature of the bond it is making. Okay, but the point is here the molecule is pretty linear. It is not straight. Yeah, it is not straight molecule, but it is in a line. You can see the carbon, hydrogen, they are although they go up and down, but they are pretty, and the way you see the molecule when it is shown to you in books is like this. You see CH3, CH2, CH2, it looks like the molecule is in one line. You know, all these atoms are in a straight line, but they are not. They are actually going up and down because of that requirement that it needs to have that bond angle. Is that clear? Okay, so this is one butanol, and we say let's check out the structure of 2-butanol. And so here is the structure of 2-butanol, and you see that now you have a OH group on the second carbon instead of first carbon. So this is definitely a structural isomer of 1-butanol, correct? Yeah, and so it has a different structure. Yeah, you can see that it is not as straight as 1-butanol, slightly bent actually. Yeah, and so you can see that this is slightly bent here. You see that it's slightly bent here. The bond is slightly pushed backwards, and that's again because of remember the oxygen has a lone pair of electron. Okay, and so these lone pair of electron are pointing downwards kinda, and these because of that these lone pairs of electrons are going to push these it's going to push this carbon from that carbon, from these two carbons, and as a result this is going little back. Yeah, now even if you consider that it is a straight molecule, which it is not, still you can see clearly that there is going to be a difference in boiling point. Boiling point is how two molecules of or two molecules of the compound are bonded to each other. Yeah, that's a boiling point. Now here clearly this molecule has a different shape, has a differently oriented OH group, and as a result it's gonna have a different boiling point than 1-butanol, which has a OH group which is pointing outward. Yeah, so the OH group is outward here. Here the OH group is not outward. It's not coming out as much. Correct? You can see that the OH group is pretty out. It's like you know, it's spreading an arm to shake hands with something. Yeah. So based on this information, can you predict which molecule would have a higher boiling point? that is correct, guys. I mean, I don't know exact boiling points of these compounds, but I would believe you can check it out. I guess you can check it out. Do a quick search on boiling points of these two compounds and give me the numbers. But I believe, based on this information, because I wasn't thinking about this question when I made the molecules, but I would believe that 1-butanol probably would have a higher boiling point. Okay. And now, because also if you look at the, if you freeze the molecule below at a very negative temperature, and so they would become solid. Okay, like the way water become ice at low temperature. So which one is that, Sahil? 1-butanol. Okay, so what about 2-butanol? Is it okay? Is it lower than that or higher than that? That's the whole question. I don't want to know exact temperature. That is irrelative. Just want to see if our prediction is right. Okay. Now same thing with melting point also. If this has more this has more organized structure than this molecule. Obviously, I would believe that 1-butanol would have higher higher melting point. So 2-butanol is lower than 1-butanol. Yeah. Yes. So we predicted it right. Yeah. And so based on the structure, we got that. So sometimes it's tricky, but sometimes boiling point, melting point is not according to our predictions, but in many cases you can predict if it's going to be higher or lower based upon your intuition, experience and knowledge and so on and so forth. Obviously there are exceptions everywhere. So as far as melting point is concerned, again, the shape of the molecule is not as perfect. Yeah, it's kind of crooked. Obviously the molecules when you talk about melting point, you're talking about how each molecule fits into the crystal lattice. Okay, the better the fit, higher the melting point. Yeah, and in this case, obviously the molecules are not linear; they are not perfectly shaped, and as a result, I would expect this to have lower melting point than 1-butanol also. Yeah, that would be my prediction. Is this information clear? Yeah. Now, what about chemical properties? Well, we said that conformational isomers, not conformational, I'm sorry, structural isomers would have similar chemical properties. They might not be identical, they are not in many cases, but they have similar chemical properties. And chemical properties are decided by the functional group, and here the functional group is OH. Yeah, here also the functional group is OH, and since both the compounds have the same functional groups, obviously their chemical properties are going to be similar. Okay, we are not saying identical because there might be a difference in the rate of reaction. As you can see, this group is out there, so it might react faster, whereas this group is slightly hidden. Yeah, slightly inside, and so it might not react as faster. Yeah, so but it will give you the similar type of products. You can give a general reaction. So if you know a reaction, let's say an oxidation of alcohol, yeah, and so we know that we can oxidize alcohol, you will get a similar type of reaction. The product may differ depending upon your starting material. So for example, alcohols will oxidize to aldehyde. Now aldehyde ketones or this type of alcohol, a secondary alcohol, would oxidize to ketone. Yeah, and aldehyde and ketone have similar functional group. Now because this is in the middle, it cannot be oxidized to aldehyde. It can only be oxidized to ketone. Yeah, here because it is a terminal OH group, this can only be oxidized to aldehyde. Now aldehyde, being more reactive, will actually undergo further oxidation to give you carboxylic acid. So depending upon how you analyze the reaction, but your reactions are going to be similar. Products may differ depending upon the position of the OH group, but the reactions are very similar in many cases. Okay, not in all cases. Okay, Alright, so let's look at now conformational isomers. Yeah, now we said conformational isomers exist because of carbon-carbon rotation bond. Yeah, and these rotations are free in nature, you know. So carbon-carbon bond rotation around these two carbons are allowed, and it happens very rapidly at room temperature. So if you ever get a chance to see a molecule, I don't know if, when we'll have enough technology to isolate one single molecule and observe it, you know, maybe under microscope or something. But if you ever get that chance, you will see that this carbon, if you hold this carbon, and if you rotate one carbon, this is going to be a constantly rotating around each other. So this carbon, let's say, is rotating clockwise, this carbon would be rotating counterclockwise very rapidly. Okay, and that's what takes place in normal circumstances. Now we said that there is a difference in energies of the different conformations, and let's see if so we said this is a staggered conformation. Okay, we said staggered conformation is the most stable conformation, and so let's go ahead and so I'm gonna rotate the carbon in such a way that or this molecule in such a way that we're gonna overlap this carbon over the second carbon. Okay, so we're gonna overlap, and here you go. Alright, so you got a staggered conformation. Now this is the best case scenario for this molecule, and the reason is you see that these hydrogens are equally apart from each other. Okay, there is no repulsion from these hydrogens. I mean, there are repulsion as a result of that. They are equally apart from each other. Okay, this is the lowest energy conformation for ethane. This is a staggered conformation. Now you probably will think, well, why does it matter? Because these hydrogens are actually still far from each other and there should not be any interaction. But if you view the molecule in which I'll show it to you, if you view the molecule in a natural state, in a ball model, now this is a ball and stick model. Okay, and I'm gonna convert this into space filling model, and when you see that, you'll see that the atoms are far more closer to each other than this type of model. Okay, this is for our simplification so that we can actually see the models, each atom and how they are connected, because a space filling model does not give you that information. Okay, but actual molecule is going to, hold on a second, let me see, where is it? Yeah, actual molecule is going to, I probably need to make a shortcut for these things. Yeah, so actual molecule is going to look like this, correct? So you can see that these hydrogens and these hydrogen are very close. So you can see that these atoms are pretty much, you know, there is a bond, single bond between these two atoms, and this is your actual space filling model of ethane. And you can see that, you know, these hydrogens are equal distance from each other. Yeah, and there is a gap between hydrogens of one carbon, hydrogens of other carbon. Again, these atoms are not according to the rule, basically. So there is a chance that these hydrogens are much larger than what they are actually, but you know, it gives us an idea that there is a very little space between the hydrogens of the molecule. Alright, now let's see the same for ethane, and now we're going to see the eclipse conformation and see if that is why this is a high energy conformation, why it is less stable. Alright, so now we're going to rotate in the same manner. Yeah, and we overlap, and here is the situation. Now you can't actually see the hydrogens that are behind. Yeah, let me see if I can give it a perspective. Yeah, so these are the hydrogens ahead of you, the hydrogens behind are hiding there. Yeah, and you can see that there is an overlap of this hydrogen over that hydrogen, and therefore this is an eclipse conformation. Okay, now let's say the space filling model for this one and see if we said, and so many times students don't understand that, you know, this is not an actual model. This is not how the molecules actually look. Yeah, the bonds are not like a stick between the atoms. Yeah, it's the bonds are, these two round things are, you know, they are invading each other's space, and that's how the bonds are formed, right? The orbitals overlap. The orbital of this carbon is going to overlap with the orbital of this carbon, and so this is a, these are p orbitals, and I think I gave you the little information, the little secret. I think I revealed that there are 4 types of orbital. There is s orbital, there is a p orbital, there is a d orbital, and there is a f orbital. Okay, there are 4 types of orbital. The elements that we need to worry about probably just falls into s and p orbital, and there is a d block element right in the middle. Yeah, some of them. But so the p orbital of this overlaps with the p orbital of that, and then the p orbital of carbon overlaps with the s orbital of hydrogen. Now p orbital is slightly elongated, whereas s orbital spherical is round. So this round thing overlaps with the little bit of bulge from that carbon. Round thing overlaps with a little bit of bulge from that carbon. That's how the bonds are formed. Okay, so let's see the space filling model, and here it is, and you can see now the carbons are barely touching each other. Yeah, there should be a huge steric well, in this case it's not huge, but you can, you know, there is a interaction between these hydrogens, and obviously this is an eclipse conformation. Yeah, and it's not stable. Yes. Yeah, it looks fat, right? And fat is ugly, you think. Yeah. This is like a full-size model, I guess, rather than skinny model. Alright, so this is eclipse conformation. Let's look at staggered. Now we saw the staggered conformation. Now let's look at the for ethane there are only 2 conformations. Yeah, staggered conformation and eclipse conformation. There is no other conformation that can result. Now let's look at butane conformation. Alright, so this is a butane molecule, CH3, CH2, CH2, CH3. Okay, and so now what we'll do is, so we'll take the molecule, and this is usually what you see again in the books. It's not linear, it's zigzag. Yeah, again the same thing as because of the required bond angle for carbon. Yeah, now what we'll do is it'll rotate. So we said, you know, we can view through carbon 1 and carbon 2. Okay, and so let's do that. If you view the carbon 1 and carbon 2, and so what you see is everything is staggered here. Yeah, similarly carbon 3 and carbon 4 are also staggered. Okay, and looks pretty nice. Yeah, and obviously there is a you can see that you see that these 2 hydrogens are kind of overlapping, but again this is on the first carbon. These hydrogens are on the first carbon, so let me see if I can mark them. Yeah, this hydrogen is on the first carbon, this hydrogen is on the last carbon, the 4th carbon. So there is no interaction between these hydrogens. Okay, and so this is a happy place for a molecule. Yeah, now so this was the situation, and this is what we're doing. Now we're going to rotate it in such a way that we overlap carbon 2 and 3. Okay, so we're going to rotate it farther down. Yeah, and so you see that there is a staggered conformation here. Correct. Now this methyl group and this methyl group are exactly opposite of this center. Yeah, and that is the reason why this is called as anti-conformation. Simply anti. It's a staggered conformation, but because the methyl groups are opposite to each other, it's called as anti. Some people call it anti-staggered conformation. I think in the notes I have used anti-staggered conformation, but it is simply called as anti-conformation. Okay. Okay. Clear on this one? Okay. Now let's see eclipse conformation for so now what we're gonna do is we're gonna rotate. Let's see. rotate this bond, okay, this carbon-carbon single bond between carbon 2 and carbon 3, and we're gonna rotate that. Now we can rotate this bond as well, or we can and we can rotate this bond as well, but it does not. It's gonna give us the conformations that we saw before with ethane. It's not very exciting, yeah. It doesn't make any difference, but we can rotate this carbon-carbon bond, and so we got this conformation. Now we rotate it by 180 degrees, okay. So if we rotated this carbon-carbon single bond by 180 degree, now this methyl group that is down is going to come up, and that's what happened. Yeah, methyl group is now up, and we have this molecule now, the shape. And let's rotate it, and you can see that now there is a overlap between these methyl groups, okay, correct. And this is the eclipse conformation. Okay, now let's check out the space filling models for both the molecules. Let's see space filling models for these two. Alright, so you can see here, not a bad situation. Oops. Yeah, not a bad situation going on. It's pretty nice, neat. Yeah, there is no none of the atoms are interacting with other atoms as strongly. Each atom is perfectly spaced. Molecule is happy. Okay, now do the same here, and here is the situation. You see that these two, so this is the methyl group, and this is the methyl group that is up. Yeah, that is eclipsing. And so you see that these two hydrogens are pretty much invading each other's space. Yeah, this is pretty much invading each other's space, correct. Oops. Okay, and so that's why eclipse conformation is high energy conformation. It is a less stable conformation, and therefore molecule is rotating around that carbon-carbon single bond, but obviously it is when it comes to this position, it basically gets a little stuck. Yeah, the energy increases, it struggles a little bit, and then if there is enough energy, it crosses. These two methyl groups are going to cross each other, and then it it quickly rotates back to its low energy state, which is the staggered conformation state. Okay. Yeah, kinda. Alright, so this is our eclipse conformation. Now let's say Gauche conformation. Okay, now here we said we have this situation. Okay, now right before this situation there is a conformation, or right after this conformation there is a conformation. Yeah, in between the staggered conformation and eclipse conformation. Okay, so let's say if you have a staggered conformation, now instead of rotating them, the carbon-carbon single bond, instead of rotating that up to 180 degree, we rotate it only up to only up to 120 degrees. Okay, that means the methyl groups, that means these two methyl groups are not going to be facing each other, they are going to be slightly off, and so you get a Gauche conformation. This is where we have rotated it only up to 120 degrees. Okay, and now if you rotate this carbon again a little bit by 60 degrees, you get eclipse conformation. Okay, so this conformation would come right before eclipse conformation, and if you keep rotated again by 60 degrees, you're gonna have methyl group right here. That is again another Gauche conformation, and so you rotate that again by 120 degrees, and you get staggered or anti conformation. All right, so that's what happening. Now again, this is not bad. This is this is bad than staggered, but not as bad as eclipse, because the two methyl groups are not facing each other, they are slightly off. Yeah, and again everything is staggered here, all the atoms are staggered. Yeah, and so this is really, all the atoms are staggered, so it's really not a bad situation for this molecule. It is second highest in energy, and second most stable in energy. It's kind of in between staggered and an eclipse. Clear? If you wanna see a space fill model for this one, let me see. That's a space fill model. Yeah, and so because these two methyl groups, let me see which one are these. Yeah, so this methyl group and this methyl group, so there is only one interaction. These two hydrogens are slightly interacting. Yeah, there is no other interaction, basically. That's it. This is the only these are the only two hydrogens that would be interacting. Okay, so this is methyl group that is slightly off, this methyl group is slightly off, and everything else is staggered though, basically. So you can see, these are the two methyl groups on this carbon. There is this these are the hydrogens on first carbon. This is the hydrogen on other carbon. You can see it at the back right there. Similar, this is the hydrogen on the other carbon, and this is oops, I can't select that. And this is the methyl group. Yes, I'm only able to select the, nope, not good. Alright, that's the carbon atom on the back carbon. Okay, are these structures clear to you guys? Yeah, this is a much better view. Gives you a decent look. Alright, now let's look at, so this was about our conformational isomerism. Now a conformer, so these are called as conformers, right? Now the next one is geometrical isomerism, and we said cis and trans. That's what we see. Now if you look at the alkene molecule, this is 1-butene. Abhishek, unfortunately this is not available as of now, because this is my software. Yeah, and this software is not free, actually. Yeah, and it cannot be shared, so that's another this is a pretty expensive software. Now there are other things that are available. I will try to find, and maybe but it's not going to be as graphically, so this is pretty Hollywood style graphics, and so it's not going to be as good looking as this. But maybe there is something. I tried to look, but I couldn't find, so maybe I'll see if there is something that you can do and rotate and see the molecules. This is called as chem drop. This is one of the chemistry, this was actually from my college. I got, so back in the day. So this is a licensed software that we get from the colleges. Yeah. Alright, so this is alkene, and you can see that alkene, so if you put the molecule, rotate the molecule in this horizontal plane, you can see that these have three-dimensional thing, but this part right where the double bond is actually planar, correct? It's like a thin plane, and as said to you, that when you have a carbon which is double bonded to another carbon, or anything else double bonded, the carbon that is double bonded has a bond angle of 120 degrees, and so that's this. So if you take this hydrogen, carbon, carbon, this bond angle is 120 degrees. Similarly, hydrogen, carbon, carbon, this bond angle is 120 degrees, and similarly this is same thing here. Alright, so any carbon that is bonded, double bonded, has a bond angle of 120 degrees. Any carbon that is single bonded has a bond angle of 109.5 degrees. So again, these are approximate numbers. They vary depending upon the situation, depending upon the bonds. Yeah, I believe this bond is slightly larger. So this, if you take hydrogen, carbon, carbon, this bond is slightly larger than 120 degrees. This is probably 121 degrees, and this hydrogen, carbon, carbon, this bond is slightly shorter. This is probably 119 degrees. Okay, something like that. There is a slight variation, but insignificant if you look at the general scheme of it. Alright, now the question is, can this molecule exist in cis-trans as a trans isomer? Can this molecule exhibit cis-trans isomerism? Yes or no? Alright, can this molecule exhibit cis-trans isomerism? That means is this a cis or trans? That's the real question. Is this a cis or trans? If you say this is cis, then can it be trans? If you say this is trans, then can it be cis? Remember that cis is where both the groups are on the same side of the double bond. Trans is where both the groups are on the other side, opposite side of the double bond. Now here there is only one group, right? I mean, the two hydrogens have the same priority. There is no problem there, and so it doesn't matter if this group is on this side or the other side. It's going to be the same molecule, correct? So you can just rotate the molecule. It's not going to change anything about the molecule. It's the same molecule. Just rotating the molecule via 180 degrees, just flipping it. Yeah? So the answer is no, this molecule cannot exhibit cis-trans isomerism. Yeah. And now let's see if there are molecules which does exist, and so you're going to see some molecules, and so we'll come back to this molecule and again explore why this cannot exhibit cis-trans isomerism. Okay, so this is trans to butene. Yeah, and you can see that if you draw a line through this double bond, we have one methyl group on one side, one methyl group on other side. Okay, again the bond angle for this carbon, double bonded carbon, is 120 degrees. You can see that this is flat. Okay, this carbon is not flat, but these carbons, the one in the middle which have double bond, are flat. Okay, their bond angle is 120 degrees. Now clearly this is a trans isomer. Yes, the two methyl groups on other side of the double bond. Alright, now let's see the space filled model for this one, and that's the space fill. These two carbons are double bonded, so you can see that there is nothing up. Okay, and so these two molecules are double bonded. There is one methyl group here, one methyl group here. Okay, so this is one situation. Alright, so this is one situation. You can see that the double bond is right here, methyl group are on the other side of this double bond. Yeah, double bond is not visible here, so you'll just have to imagine that. Alright, now let's look at cis isomer and see if what happens. So this is a cis to butene, you can see, and you can see that if you rotate it, you can see that the two methyl groups are overlapping. This is something which we saw like a eclipse conformation in alkane. Yeah, it's something like that. The two methyl groups are facing each other, and obviously from the look of it, it looks like there should be some instability issue here. And let's look at it from space filling model view and see if there are some issues with that. And so here you have there is a double bond right here between these two carbon, this methyl group, and there is this methyl group, and you can see that these hydrogens are not happy. Okay, they are pretty much invading each other's space. Yes, so this is called as steric hindrance. Yeah, these two methyl groups are sterically hindering each other's presence. Yeah, and as a result, this is high energy state, less stable in the sense, and instability is, again, as I said, relative. You need something to compare to. Okay, and so you're saying this is less stable, you're meaning that this is less stable than trans conformation. That's all you mean, that this is less stable than trans conformation. Is that clear? Okay, and so this is cis conformation, this is trans conformation. All right, now so this is about geometrical isomerism, and let's go to 1-butene now. The question is again, can it exhibit cis-trans isomerism? You need two groups of different priority. Here there is only one group that has a different priority than, so these three hydrogens have the same priority. Okay, there is this one group that has the same priority, and so it doesn't matter if this group is on this side or if you put it on this side. Just imagine you take this ethyl group from this side and replace it with hydrogen. You basically get this scenario. That's all you get. Yeah, this is the same molecule as before, correct? This is the same molecule as before. That means that these are not different molecules, these are the same molecule. You are rotating it and you're getting, yes, you rotate one molecule, you get the other molecule, and that does not mean that they are isomers. They are not isomers. Okay, they are the same molecule. As a result, a molecule like this, which has same groups on one side of the double bond, cannot exhibit cis-trans isomerism. Whereas if you look at this molecule, this is a cis isomer. Okay, let me just go back to ball and stick model. Yeah, and so this is our cis isomer. Let's do the same with this, and so you have, this is trans isomer. Okay, and can you convert this trans isomer into cis isomer? Can you? I said you cannot rotate the carbon-carbon single bond, carbon-carbon double bond. There is no way you can rotate a carbon-carbon double bond, so you cannot convert this into that. Okay, unless you break a bond between you know, at least one bond between carbon-carbon double bond. Yes, so these two carbons, you have to break at least one bond, and only then you can make a rotation. Now because they are doubly bonded, you cannot rotate, and as a result this is a different molecule, this is a different molecule. Okay, now what about their properties? Obviously they would have different chemical and physical properties because they are totally different molecules, correct? Yeah, these are different molecules, they have different names. This is called as trans to butene, this is called as cis to butene. Okay, and since they have different names, they also have different physical properties, different chemical properties. You know, their boiling point, melting point, refractive index, solubility is going to be different. The difference may not be significant, but we don't care about that. It's different is different. Yeah, and their chemical reactivity is also different. Yeah, they are alkene, so you know, sometimes, so if you hydrogenate this alkene, if you reduce this alkene double bond, you will get butane. Same thing with, you know, something with here. So in many cases the properties are going to be similar, but they are going to be different in many cases also. Okay, it again depends upon reaction to reaction. Okay, because the functional group again is same. This is a double bond, yeah, and this is a double bond, but there is going to be a difference in how they react or where they react, and so on and so forth. Okay, right, now let's look at, and we didn't discuss this in class notes, but there is also isomerism in cyclic compounds. Okay, so we'll look at, first is let's look at cyclobutane. All right, so let's look at cyclobutane. So we'll just take a structure of cyclobutane. Okay, this is cyclobutane, and if you look it from the top, it looks like a square. Yeah, that's the square. Each carbon has two hydrogens. Yeah, and it looks like a square. It looks like a square molecule from the top, but if you look it from the side, it's not a square molecule, slightly bent. okay, and that's what exactly it is called. It is called as bent cyclohexane because it has this bent structure. And the reason it is bent is because to remove that, we said that the if you imagine this molecule to be straight, because I cannot draw a straight molecule, yeah, this software cannot draw a straight molecule, and so if it would be straight, these hydrogens would be overlapping, correct? These hydrogens would be overlapping, correct? These hydrogens would be overlapping, so everything would be eclipse if this is a straight molecule. Second problem, what is the bond angle here between this carbon, carbon, carbon? What is the bond angle here, and how much it is expected to be for a singly bonded carbon? Okay, it was expected to be 109 degrees. It is 90 degrees, correct, Abhishek? There is a huge deviation from its natural bond angle. That means this molecule is at strain. If it is a square molecule, there is going to be a huge, it is called as angle strain. Okay, there is a angle strain. That means you have something natural, you are trying to bend it, and as a result it's gonna be under stress, yeah, and that strain is there. Now by assuming a bent structure, it bends a little bit, so that now you can see that this bond angle is not 90, it's actually slightly more than that, correct? Similarly here in this case, it's this bond angle is slightly more than 90 because of that bent structure. Okay, so the molecules do these tricks to get rid of those angle strain. Okay, now by doing that, it has gotten rid of two things. First thing, it is not perfectly eclipsed anymore. That means there is some reduction in energy there, plus the angle has increased, and so that helps, yeah, angle has increased, and that there is also reduction of that angle strain. So this is much stable molecule in if it would be a perfectly square molecule. Yeah, it is not, and as a result its stability increases by a little, so it can actually exist. Alright, now don't want to save, no, let's go to cyclobutane. Now we're gonna where is it? Yeah, so now we're gonna replace one of the hydrogen with with methyl groups. Okay, and so if you have that situation, so if you replace any hydrogen that is on the top, okay, any hydrogen that is on the top, you get two methyl groups that are also on the top. So let me put that in a proper place here, give me 1 second. So you can see that these two methyl groups are on the top of the molecule. They are, both of them are on the same side of the molecule, or same side of the plane of the molecule, and therefore this would be a cis isomer of cyclobutane. Yeah, similarly, if you draw the molecule, now in this case you can see that one molecule is up, one methyl group is up, the other methyl group is down, and this is the plane of the molecule, a straight line right here. Okay, and this is the straight line, this is the plane of the molecule. This methyl group is above, this methyl group is below, and therefore this is a trans molecule, and you can see the structure right here, it is shown like this. Okay, now obviously from looking from this we can predict that this molecule is more stable, this molecule is less stable. Now we said that cis-trans isomerism exists in this molecule because there is a hindered rotation around carbon-carbon single bond, similar to we saw with alkenes. Yeah, you cannot rotate carbon-carbon double bond. Similarly, you cannot rotate this molecule. There is no way you can rotate this molecule. This molecule can flip. Yeah, it can invert, which is going to be the same basically, but you cannot rotate just one single bond. Yeah, it's gonna you're gonna have to flip the entire molecule. Okay, So understood, cis butane is less stable than trans butane. Okay, similarly we have cis pentane. Again you can see that this is if you look at the pentane, this ring right here, it is not, you know, perfectly, you know, the way it is right here in the structure. You can see that it is shown to be a perfectly planar ring. It is not planar at all. It is actually quite bent, similar to butane. And the reason is again same, to avoid that angle strain, it becomes a little bent structure. To avoid eclipsing of the hydrogens, you know, so this is, you can see that these hydrogens are a little eclipsed, and so to avoid the eclipsing of the hydrogen, it becomes a bent structure. Okay, so it is a bent pentane ring, and this is a cis 1,2 dimethyl cyclopentene, sorry, cyclopentane, and because both the methyl groups are on the same side of the ring. Okay, obviously there is going to be interaction between these two methyl groups, and as a result it is less stable if you compare that with trans cyclopentane. So here is again cyclopentane, this methyl group is going up, this methyl group is going down, and as a result it is more stable. Yes, you can see that this is the way it is been shown. Yeah, this will give you a great visualization of organic molecules. You should be able to visualize organic molecules, because without that organic chemistry is no fun. Alright, similarly let's see cyclohexane. And so this is a cyclohexane molecule. This is the way you usually draw cyclohexane. Now in reality, is it like that? How does it look in reality? Well, I'll show you. Here is a cyclohexane, completely different look from the side. Okay, it is not straight at all. You can see that it's completely bent at various points. Okay, this is actually called as a chair conformation. Now even cyclohexane can exist. For this, Abhishek, cyclohexane. Okay, alright, no issues there. That's a space film model for it, very little use to us. Yeah, but so here is if you look it from the top, yeah, if you look it from top, what you see is there are 6 carbons, 1 2 3 4 5 6 carbons. Alright, these are the hydrogens that are going up, these are the hydrogens that are on the side, and below this, so below this carbon there is a hydrogen, below this carbon there is a hydrogen, below this carbon there is a hydrogen. Okay, and so if you look from the bottom, it's going to look like this. It's look like a disc. It looks like a disc to you, correct? It looks like a disc actually. Let me hold that clear. Yeah, but what you need to realize is that this carbon is slightly up, this carbon is slightly sorry, this carbon is slightly down, this carbon is slightly up, this carbon is slightly up. Sorry, this is slightly down, this is slightly up, and that is again done so that it can get rid of that angle strain and get rid of this eclipsing. Yeah, and so this is really not much use to us. Yeah, so that is the reason why you know, ball and stick model is perfect for studying any molecule. And so this is our cyclohexane. Okay. All right, so this is, let me rotate it properly so that I can actually show you something. Nope. Yeah, sometimes it's just hard to rotate the molecule. I think it's one of those days. I'm usually good with this thing, but I think this is the best I can do right now. Okay, now what I want you to realize, this is actually called as chair conformation. Now this can actually cyclohexane can exist in various different conformations. Okay, so this is called as chair conformation, and you can imagine it like this is where you would sit. Okay, this is where your back would go, and this is just something like an extension. Okay, so this is called as a chair conformation. Yeah, does it look like a chair to you guys? Yeah, this is slightly inclined, but you can, if I could rotate it a little bit, I guess I would would look like more like a chair. Yeah, this would be the place where yeah, yeah, so this is not, this is something like an accessory or something at the back, but so it looks like a chair like here, and so it does, and that is the reason why it is called as chair conformation. Now if you put, if you take this carbon, rotate it slightly, you get a boat conformation, because you'll have a shape that looks like a boat. Okay, I don't have, I haven't drawn it here, but there is also a boat conformation. There is a half chair conformation, where this back is completely straight, and then you also have half chair conformation, boat conformation, twist boat conformation, and chair conformation. Okay, there are these 4 conformations of cyclohexane that needs to be studied. All right, so this is a chair conformation. This is the most stable conformation for cyclohexane, and the reason is, again, the bond angle, how much it should be. What did we say? What is the natural bond angle for carbon that is single bonded? Abhishek, that is fine. I guess if you not get knocked out. 109 degrees. Yeah, and so obviously it should be around that. If it is like this, yeah, if it is a cyclohexane, if it is a straight molecule, then the bond angle would actually be much larger than that. Okay, but to avoid that, it becomes a bent molecule like this, and now the bond angle is 109 degrees, exactly 109.5 degrees. If you look at the the conformations of these molecules, these atoms, yeah, you see that this is staggered, this are also staggered, and you can rotate in any direction, you'll get a staggered conformation. All the atoms are staggered. Is that clear? Yeah, and this is the reason why cyclohexane is a stable conformation. That's the reason this is the most stable conformation for cyclohexane. Alright, now let's replace one of the 2 groups, any 2 hydrogens, with methyl group. Okay, so we'll take any 2 adjacent carbon atoms, adjacent hydrogen as atoms. Now up till now we have said there are 2 conformations, cis and trans, and which one is more stable? Is it cis or trans that is more stable? Okay, for cyclopentane, cyclobutane, we said I showed you 2 conformations, cis and trans. Which conformation was more stable? Abhishek? Trans conformation, correct. Now is that the case every single time? Well, not really. It depends. It really depends which molecule you're talking about, and there are a lot of other factors you need to consider. Sometimes it is not the situation. Okay, and I'll show you later on a conformation where the cis is actually not stable conformation. Okay, so this is cyclohexane. Now remove any two hydrogens, replace any two hydrogens adjacent on adjacent carbon with methyl groups, and so here in this case we got a cis conformation. You can see that this is correct. So this is a methyl group that is going up, this is a methyl group that is going up, and so this is a cis conformation. Yeah, and now here in case of cyclohexane, it is very different than assigning conformations in other cases. How you assign a cis and trans depends upon the relative position of the group. Now here we are saying this methyl group is up as compared to this hydrogen. Okay, so this methyl group is up relative to this hydrogen. Okay, similarly this methyl group is up relative to this hydrogen. Okay, and since both the methyl groups are up relative to the hydrogens on the same carbon, this is a cis conformation. Okay, so this is, you can see, so this is a cis conformation. You can see the methyl group on the top, this is actually on the side. Okay, it's not actually on the top. Okay, that's the way the methyl groups are. Yeah, now let's look at the trans conformation. This is the trans conformation. Yeah, now here this methyl group is down as compared to this hydrogen, correct? Similarly this methyl group is up as compared to this hydrogen on the same carbon. Now because they are in different orientation, they are, this is up and this is down, therefore it is a trans conformation. It's not their position relative to the ring, it's their position relative to the hydrogen on the same carbon. That's what you need to look for when you look at cis and trans conformation. Yeah, and obviously here in this case trans conformation would be more stable. Okay, and it's not the same reason as we studied before, it's a completely different reason. And usually if you look at cis conformation, you see that a methyl group is up, yeah, whereas this methyl group is on the side. And if you look it from the top, it becomes more evident that this is actually on the side, it's going outwards towards the ring. Yeah, out is going out in the space, whereas this is up. Yeah, and this is a cis conformation. Okay, and we expect cis conformation to be less stable, but this is not because of the same reason, this is because of different reason, because any group that is up in a cyclohexane conformation is actually less stable. Okay, so because this methyl group is going up, this conformation is less stable, whereas in this one both the methyl groups are out. You can see that this is going out in the space, this is going out in the space, and therefore these methyl this is a stable conformation for cyclohexane. Yeah, let's see if it makes any difference in space filling. Yeah, it's ugly. Alright, okay, now here is a different situation. Now I have labeled the methyl group with a different color. Okay, this is anti-methyl group, this is anti-methyl group. Now this is, again you can see this is a cis conformation. Okay, and if you look it from the top, you see that they are going out. Yeah, and this is on 1 and 3rd carbon. Yeah, this is not on 1 and 2, but this is on 1 and 3rd carbon. So this is obviously a cis conformation because they are cis, because if you look at the methyl group, it is up as compared to this hydrogen. This methyl group is up as compared to this hydrogen, and therefore this is a cis conformation. Okay, and since they are going up out, it is stable. Let's look at the trans conformation. Now what we'll do, is take one of the methyl group and replace it with the hydrogen, and so here is the situation. Yeah, is this oops, I think I made a mistake in doing that. Yeah, so this is a different situation. Yeah, and so now, sorry, yeah, not a mistake. So this is one case. Now you can also have, you can also have these hydrogens as methyl group. Yeah, you can exchange the position, and you can flip the ring, and when you do that, actually the position of the methyl and hydrogen changes. Okay. um, so what is happening here is we assigned these specific hydrogens as methyl, but you can also assign these hydrogens as methyl. Okay, correct, these two hydrogens as methyl, and so in that case you're gonna get this situation. Yeah, so this methyl groups are going down, or you can say these methyl groups are going up. Okay, obviously this is a bad thing, correct, both the methyl groups are going up, and that is not a stable thing. Whereas this, in this case, both the methyl groups are going on the side, and it is a good thing. These are the same molecule, these are not different molecules, this is the same molecule, both of them are cis. Okay, and this happens, you can imagine that this is a situation in one case, and in next fraction of second molecule flips. Okay, and you get this. Okay, again the molecule flips, so it goes like from this conformation to this conformation to this conformation to this. So it's flipping, it's nothing is happening, you're flipping the molecule. So these are the same molecule, these are not a different molecule, but this is obviously much less stable because the two methyl groups are up. Yeah, whereas here the two methyl groups are on the side, and therefore this is much more stable. Okay, so molecule is going to spend most of its time in this conformation. But let's talk about trans, if that actually changes situation. So this is a trans molecule, same a different molecule. Yeah, and so we now here we have two methyl groups on first and third carbon, and they are trans. This is down as compared to this hydrogen, this is up as compared to this hydrogen. So obviously this is a trans molecule, trans cyclohexane. Now is it stable than this? So this is one situation. We had cis, where the two methyl groups are going out, and so obviously this, we said this is stable, whereas in trans you can see that again one methyl group is up. Okay, so obviously this is less stable than cis conformation. Yes, this is okay, this is going out. Okay, and so this is, since this methyl group is going out, this is fine, but this methyl group is going up, and as a result this is not okay, this is less stable as compared to this conformation. Okay, so if you're talking about 1,3-dimethyl-cyclohexane, the trans conformation is actually less stable than cis conformation. This is one example to show you that it is not always that cis is less stable. Okay, sometimes depending upon the situation, cis can also be more stable than trans conformation. Okay, yeah. Yeah, and this is something that I don't think any book would explain to you. Let me tell you that you can search for books that would actually give you this explanation. It won't, and the reason I know is because when I was doing my PhD, I think until up to the half of my PhD completion, I did not know this thing. I used to, I mean, I know there are cases where there could be cases where cis conformation is more stable. I didn't know a specific example unless I started playing with this, and it actually came up with I was taking a class with one of a professor, a brilliant professor, and he used models to make the model, so to make the molecules. And I think he mentioned that this is a situation, and I was very curious exactly what is going on. So I started making model on the software, and I found out the reason for it. And so this is the reason. That is one example where trans is actually less stable than cis. Okay, I believe there are other examples in some cases. So that's my idea of why why that is the case. And it's just nothing about it's not a hard rule in chemistry that trans are more stable than cis. It just depends upon the structure. Yeah, so that's what you need to be looking at. Not it's a good idea at this stage that you can generalize, but if you are doing a specialization into anything, basically generalization does not work, because a specialization is study about specific things. Yeah, exceptions, that's what you study, and that's what gives you more knowledge about anything. So if you are doing specialization, you should obviously looking for uh, exceptions, not generalizations. Okay. Okay, I think that is it from my end. um, I don't know why this is, yeah, nothing. Same thing here. This is trans cyclohexane. This is also trans cyclohexane. Okay, any questions?